Hi, my name is Nicholas Dwork, and today we're going to be discussing the anti-aliasing filter of MRI. Recall that MRI is a Fourier sensing modality, so we collect data in the Fourier domain, and if we collect enough data, we can just perform an inverse Fourier transform to reconstruct the image. A reminder, this is the spin warp trajectory. Here we're collecting vertical lines of data in the Fourier domain, and while the Fourier domain extends off to infinity, we can only collect a finite amount of data. So the question is, how do we prevent errors when collecting just this smaller amount of data? To answer this question, let's look at just one horizontal line of Fourier data. We'll plot it as a graph as shown here. So this is the spectrum in the Fourier domain, and this is the corresponding function in the space domain. Here we're assuming that the image in the space domain is compact, it's bounded. Collecting data in the Fourier domain corresponds to sampling, and sampling can be thought of as multiplying by a comb function, this set of arrows, evenly spaced arrows. Multiplication in the Fourier domain is equivalent to convolution in the space domain, and the Fourier transform of the comb function is itself a comb function. These comb functions are related by their spacing. The spacing between the deltas in the Fourier domain is equal to the inverse of the spacing of the deltas in the space domain. So what we get in the Fourier domain are a weighted set of deltas. These are our samples. And in the output, we get the space domain function convolved with this comb function, which is just replicas of the space domain function. And we see that as long as 1 over delta is greater than the width of the space domain function, then the replicas don't overlap. We can simply isolate the center replica, and that's our reconstructed function. This tells us that the lines in the Fourier domain must be closer than the inverse of the width of our object in order to avoid aliasing. Now I'm going to show you what happens if the lines get too close. Here I'm using data that was shared with the eSpirit paper. And currently what you're seeing is a reconstruction with the fully sampled data set. Now I'm going to increase the distance between the lines by 20%, 40%, 60%, 80%, and 100%. And you see that we get these replicated copies of our original image encroaching in from the sides. That's aliasing. So you want the vertical lines of data in spin warp to be close enough to avoid this error. Okay, so that tells us about the horizontal direction, but what about the vertical direction? The body extends far beyond the image here. Why don't we have aliasing in the vertical direction? To answer that question, we're going to look at just one column of the Fourier data. Again, we'll plot it as a function. This time, though, the space domain function extends far beyond some minimal width. And so if we were to just sample in the Fourier domain like before, we would necessarily get aliasing in the space domain, and that's what we'd like to avoid. We want to multiply by a window that isolates the portion we care about. This is what a window might look like. It's fairly flat near the center of your field of view where you care about what you're looking at, and it goes to 0 as you get farther away. And so here's the result of multiplying the space domain function with the window, and as you can see, we now have a width. This function goes to 0. Now we can use the sampling theory we previously developed. But where does this window come from? To answer that, we need to go back to some fundamental electrical engineering. This window is a low-pass filter. It's high near the center, and it goes to 0 as you get farther away. We need to apply this window before we do any sampling. And the way to do that is to apply the window with electronic hardware. So here's an antenna or a coil that you might use. This is one currently sold by Siemens. Out of this antenna will come 2 wires. One goes to ground, and the other goes to the low-pass filter. Now this is a very simple low-pass filter. It's made with a single resistor and a single capacitor. So probably true MRI machines use ones that are much more sophisticated than this, but this illustrates the point. That then goes to an analog to digital converter, otherwise known as a sampler, and the sampled data is what goes to the computer and is stored in memory. This low-pass filter prevents aliasing, and because it prevents aliasing, this filter is called the anti-aliasing filter. So that's how we get an image like this. And now that you're looking at it with fresh eyes, you might notice that the image is brightest in the center and gets darker as you go near the top and bottom edges. That's the effect of the anti-aliasing filter. We apply an anti-aliasing filter in the readout direction. We make sure that our lines are close enough to avoid aliasing in the horizontal direction, and that's how we prevent aliasing with the spin warp trajectory. Thank you for your attention.